Okay, now we are recording. Good. So today I just want to do an introduction of the course. So you don't have to actually take any notes or anything. Just sit back, relax. It's just going to be about what this course is about, okay? And everything that we say, we're going to repeat it, okay? So I first want to start by introducing the team that you will meet during this course. So first of all, I'm Julia Zavadlao. I'm professor at TUM School of Engineering and Design. And I have a group which is called Multiscale Modeling of Fluid Materials. And if you are more interested in what we do, you can check out our webpage. But in general, we try to use machine learning in the domain of molecular modeling and molecular simulations, or like on this level of designing molecules from what's called bottom up, from like a molecular design. And I will give you during the course and also today, I will give you some examples also from our group so you can see what we do, but I will also go through other fields like fluid dynamics to other like engineering applications to, I don't know, aerospace, car or whatever, so that you get a feeling of where machine learning can be used in your domain. I think most of you are either from engineering kind of courses or physics or something like this. So I will try to cover the areas that might be like interesting or relevant to you, okay? So I will be having lectures, so you will see me in the mornings. And then for the exercises are going to be held by Anna. She's sitting over here. You will meet her today at 12, right? And she will be with you during the exercises. And then for the exam is mostly prepared by my PhD student, Sebastian. Of course, I check everything, but if you have specific questions about the exam or review exam or corrections and something like this, is the best person to contact. Also, in terms of theses, a lot of the times we get emails from people they want to do thesis at our chair. It's best to contact him or anybody else in like any other PhD person in my group. Okay, good. Some more people joining. So like I said, today, I just want to give you an overview of what this course is going to be about, right? What are you going to learn here? So today, what we are going to talk about and discuss is like to get clear what some words mean, like what is machine learning, okay? To have some kind of an idea, and what is deep learning, or how do we distinguish that too, or how do we distinguish this from artificial intelligence. And then we will talk about what kind of classes of machine learning algorithms we have and what is their typical task, okay? So we have categories, let's say, of methods, and we will look into that. And then we will try to come to the other part of our title of the course, right? It's physics-informed machine learning. So after we have cleared the machine learning part, we will look at, okay, what does this physics informed mean in the title, okay? And in particular, we're going to look at, we want to use machine learning not, to create a deep fake video or to, I don't know, create an image or something like this. We want to use it in our scientific domain where we have physical rules, okay? So we're going to see how we can connect that and how this comes into play, particularly in engineering, in physics, chemistry, whatever you want to call it, or science in general, where we want to obey strict rules, right, that we know are correct. And we would like machine learning to also obey those rules. Okay, and then I will give you some examples. There are so many examples nowadays. This is an exploding field, right? So I just want to give you a sample of examples so you get a feeling of what has been done. Okay, and today you don't really have to understand how this works, right? We will come back to them during the course, and some of these examples we will actually do during the exercises, so you will get to know it. But today is just, what can be done with machine learning. Okay, and then after we have discussed all this, we will look at what we're going to learn in this course, because we cannot cover every kind of method algorithm out there. So we have to restrict ourselves. So after I have introduced you what is out there, I can tell you what you're going to learn. Okay, so that's why we take this approach. So I will tell you then something about course structure, content, how the course is designed, and some like organizational things like Moodle, literature, and stuff. All right, so let's start. And to get you involved a bit, we're going to start with a quiz, a short quiz. It's not something difficult, okay? But just to wake you up a bit, okay? So we're going to have a short quiz with only 2 questions, okay? And the first question is this one. Task 1 that you have to solve, that is what is the number on the image. So on the next slide, I have an image, and there's a number on the image. You have to tell me which number you see on the image, and you have to do this as fast as possible, okay? It's clear? Yes? Ready? 3, 2, 1. 8, okay. So the number is 8. Yeah, I saw it's easy, right? Okay, now let's do another question or another task, okay? Now I ask you to solve this task, which is the number, I will show you the number on the next slide, and is the number a prime number? And I wrote in the parentheses what the prime number means, so in case you don't know, so you can read, okay? And again, the idea is try to answer as fast as possible. Ready? Yeah, you can take a guess if you don't know. It's a 50-50, so it's a good chance you will guess. Nobody. Somebody has to say something. Come on, it doesn't matter if you say it's wrong, correct? Doesn't matter. Yes, it's yes. The answer is yes. Okay, but it took you quite some thinking or guessing, right? Okay, so why did I bring these 2 questions, right? I want to discuss what is the difference between these 2, okay? So how did you solve the task? Or if you would explain it to, I don't know, your neighbor or somebody else, how would you say how to solve the task? What instructions would you give to your friend? How to solve task 1? And what would you say for task 2? Yeah.
2 circles connected vertically.
Yes, but that rule, right? You propose a logical rule, right, to check. Yes, but yeah, that's how you think. Okay.
Somebody doesn't know what the name is.
Yes, but what if I rotate the picture? Then
excuse me?
I can rotate the 8, still 8. Yeah, I can rotate it around 360, right? It's always number 8, but the 2 circles are no longer vertical.
Yeah, for me, then it is not an 8 anymore if it's horizontal.
But it's still a number. Yeah. Like if you have to choose which number you see, right? Or if you ask, like sometimes we don't, just like image recognition, right? Sometimes we don't write straight, right? We write in the, I don't know, all sorts of things, right? So if you give a rule, like it has to be one above the other, you're going to have cases where this is not going to be recognized. Okay, how about the second one? Yeah, there's a hand there, no? The second one should be easy, right? Yeah.
There's no 2 numbers that can multiply each other, like 2 numbers.
Yeah, so we can do a logical test, right? Okay, so in the first image, right, you have image recognition. Basically, you knew that this was an 8 as soon as you saw it. And honestly, if you talk about a thought process, how you figure this out, you figure it out faster than how you figure it out. You don't even think about how you figure it out, you just know. And for a lot of things that humans are solving, that a task that we are good at, we just know, we recognize it, and we don't exactly, for every kind of case, know why. You can pose some kind of logical rules, but these logical rules you can always find certain exceptions, right? When this would no longer be true. On the right hand side, we have this task of prime numbers. Here we have a well-defined problem and well-defined logical rules. I can check, is this number divided by 2? No. Then I say, okay, let's go next. Is this number divisible by 3? No. Is this, and so on and so on and so on, right? And then if all answers are no, I can say this is a prime number and this is a definite answer. There is no exception to this case, right? So now when we come, so this is us, our brain. Our brain is like, also a machine, right? If you think about it like this. But now let's come to the, in silico brain, okay, our computer algorithm. And let's think about, from the perspective of a computer algorithm, how fast it is to solve, or how easy it is to solve these two tasks. Okay, so in the case of prime numbers, because I have explicit rules and this is very defined, I can write an algorithm very easily with my if and for statements, right? And this is going to work 100% every time, 100% correct. And this algorithm is going to be solved in a computer way faster than you can ever imagine to think this, to solve it, right? Unless you memorize the prime numbers. So the computers for this kind of problems on the left-hand side, they are much faster. It's straightforward to program them, and humans will never beat computers, right? For number recognition, or in general image recognition, we don't know what kind of algorithm to write, right? Because we don't know how to propose logical rules with the statements, with for loops, while loops, and if kind of statements to check logically if something is an 8 or a 6 or what, right? So it's super hard to write this part, okay? And that's why we need a new kind of algorithm, right? An algorithm that we don't explicitly have to program. We don't have to write if statements, but the algorithm learns on its own, okay? So for this kind of task, we need that are super easy for us, are kind of hard for the computer because we don't know exactly how to program it. And this is where our machine learning comes into play, typically. So now let's look at what is this difference between these three names that you already probably saw a lot in the media, right? So you have artificial intelligence, we have machine learning, and we have deep learning. So what is the difference? So typically, artificial intelligence think of as a whole thing of everything. And it has to do with any kind of computer that tries to mimic human behavior, right? We try to get a computer to be in certain tasks as good as we are, okay? Or try to fool us that we are talking to a human, not to a computer. Okay? Then as a subfield, we have machine learning. And machine learning is any kind of algorithm or method, model, whatever you want to call this, that has the ability to learn without being explicitly programmed, okay? So this is like image recognition. This without being explicitly programmed means I don't write for loops, if loops, I don't write some logical statements, right? But I propose a model, and the model can learn somehow to figure out that an image of an 8 is an 8, okay? Or you have this example of how to distinguish the emails that you get in your inbox, right? If they are email or spam, right? It's also not something that you can really easily write logical statements, when something is a spam. And then as a subfield of machine learning, we have deep learning, okay? Deep learning means that we are just using models, our models are deep neural networks, okay? So it's a subclass of machine learning where any kind of model will replace with a neural network. It's just the use of neural network, okay? Now, in the course, during the course, we will learn all about neural networks, right? But for now, you see some circles and some lines. Okay, so it's not important to understand it now, but this is how we represent how the model of neural network looks like. Okay, this is how we picture it in the mind. To know what kind of model neural network we're talking about, we draw it with circles and lines. That's all you need to know at this point. So it denotes some kind of architecture of the neural network. And the deep in this deep learning just refers to the architectures that are deep in this direction. So you have this direction, right? We stack circles in this direction. And if we have an architecture like this, it's deep. And they figured it out that if you have architectures like this, which are not deep, they are not so powerful as the ones that are deep, which are more powerful. Hence, we have like this deep learning, okay, being like very powerful method. Okay, good. So now that we know this distinction, let's look at what is similar to humans, okay? Where do we have similarities? So what we will, maybe I should also say, what we will do in this course is machine learning, right? We will not talk about artificial intelligence. We're not interested to fooling anybody that, we are dealing with a human, okay? In fact, what we will be doing is just algorithms. You see, it's far from, ever being human intelligent, okay? In fact, probably in doing the exercise, you will figure out that this can actually be very stupid and so far from intelligent. And you need to work for it to make it, a bit intelligent. Okay. But there are some similarities to humans, right? So first of all is how these models learn and how we learn, okay? So we have the similarity in terms of how we learn, and we both learn through data, right? So if you think about a kid and how the kid learns to know that letter A is a letter A, right? You present the kid with a picture of a letter and you say, this is A, right? And you do this repeatedly, right? And at some point you ask the kid, okay, tell me what is this letter? And the kid says, I don't know, A. And then you say, oh, good boy. Okay. If not, then you say, no, it's not B, it's an A. You're correct. Okay. So basic principle is to show data. If the answer is correct, you reward. If it's not, you basically correct. Okay. And you will see that all of these machine learning algorithms, they learn also through data in much the same way. We represent data to the machine learning algorithm. And if the algorithm gives us a wrong answer, we say, no, this is not correct. You should, correct yourself. Okay. But we don't, so this is in respect to not directly programming the model or us, right? The parents don't actually tell our brain how to connect the neurons to each other, right? That this will work, right? In the same way, we also don't exactly tell the model how it should figure something out. Okay, and then the next thing that I want to discuss here is in the media, you will have a lot of the times this comparison of machine learning to black box kind of models. Black box is this is kind of a metaphor where a black box model is a model where I give some input to the model and I receive some output at the other end. And I have no idea what's going on inside. So this is completely close to me. I have no idea what's going on. So I think this reference to the machine learning being black box is not true. Okay, and you will see in the course why not. And in fact, in this course, we will open this box and we will look inside. Okay, so I think a very better reference would be to say that machine learning is a very open, transparent box where you can see inside. Because we know for machine and these models, we know how every piece of this model works. Okay, it's just functions. You will see. It's nothing magical here. Okay. It's something that we know quite well what it is, right? The thing is why this black box metaphor was introduced is because when you put a lot of components together, you can get something very complex. Okay, so we know each part of, if you think about each wheel, right, we know exactly how it works. But if I put like millions of them together, then it's like such a complex behavior that it's hard for me to know how this works together. Kind of like in your brain, right? You know, nowadays, I mean, we know for every neuron how it works. There's no also magic there, right? We know that the neurons are connected, signals travel, all that, right? But your brain has like millions or billions of those. And then collectively, right, this is something that is hard for us to figure out. So this is another parallel to the human behavior. Okay, so now let's go through these different types of machine learning. So the first kind of category that we have is the so-called supervised learning. And then we have two more kind of types of machine learning methods, and they differ in the things of how they approach a problem and what kind of task they are solving. Okay, so in the first one, supervised learning, we learn the output given the input, and we have labeled data. And the typical tasks that we are solving are the task of classification and the task of regression. So I will now explain what all of this means, right? Let's first start with what is labeled data. Okay, it's very intuitive, okay? Labeled data means that I have some database, right, that I use, and this database is used to train the model. So, or the model to learn. This is called training in machine learning. So we might have some images of fruits, and for each image, which is an input to a model, we're going to label it here and say this is an apple. Okay, so Y would be our label. Okay, and then we use this in our training kind of phase of learning. And then when we have the model trained, we of course want to use it to predict some new image for which we don't know what is on the image. And then, so this is called the prediction phase. So then we have some new image, but for this image, we don't know what is on the image. And then we ask the model to predict basically the output or the label here. So these labels are also outputs or labels. Okay, so this is the labeled data. So we have this. And now we want to look at this task. So we have two basic tasks in supervised learning. One is the task of classification, and the other one is task of regression. Okay, so let's look at this. So we start with task of classification. And I give you an example. An example of this task would be a question: will I pass this course? Okay. So we ask the machine to give us an answer, and this is a task for a machine learning model. Okay, so how would this go? Okay, well, first I need to get some data, right? Training data in order to train the model. And I might, let's say, collect the data from last year's students, right? How many hours they were studying, how many lectures they attended, might put this into a table, and for each one of the students, I know if they passed or failed. So we have this pass or fail kind of labels for each data point, which here is a student, right? And I can also plot this, right? And then these red ones are all the failed ones, and these are all the blue ones are all the ones that passed, okay? So what machine learning tries to do here is that it tries to find what's so-called decision boundary, this green line, tries to find where this green line should be placed such that all points will be correctly classified, okay? And once we have the model trained, then the idea is that you can use this decision boundary for predictions, okay? So how this works, I have then, let's say for you, you ask a model, I have studied attended 10 lectures, studied for 10 hours, tell me if I will pass or fail. And then the machine learning would just look at where is this new point? Is it on right-hand side or left-hand side of the decision boundary? So in this case, it's on the right-hand side. And so the answer would be you will pass. Okay, so this is how it works. Now, why is this called classification? Well, because we are predicting a class, right? So this is a distinguishing part, is that the output, so this is how we distinguish classification to regression. The output is discrete, okay? And it's an element of a finite set, okay? It's a class, as the name suggests. So here we have just two classes, okay? So this means a finite set. So we have a finite set of classes, and we have to predict in which class it is. Okay. Good. So regression, on the other hand, is when we have the outputs. Okay, here the outputs are continuous numbers. Okay, it's not a class; it's a number, continuous number. Okay, so we can modify a bit the previous question or task to the new one, which is how many points you will score on the exam. Let's consider that you can get any kind of point, like any kind of number on the exam. Okay, so in this case, we would also collect some training data from last year, right? We would get some points. So these are blue are the points from the data, right, from previous year. And what machine learning would try to do in this case, it will try to find a fit like this green line. Okay, a fit to this data, basically. Data fitting, or function fitting, you can call this. Okay. And so after the model is trained, we have found this green line or function. Then we can use it in order to ask this question. So let's say you have 10 and 10 lectures, right? And then basically you put into the machine learning model 10 and you read out the value of this function. And this is your output, okay? Function fitting. Good. So these are the two basic tasks of supervised learning. Now we move on to unsupervised learning. Unsupervised learning is all about finding low-dimensional representation of the input, or maybe find some patterns in the data. Now, what is distinguishing point is that we don't have labeled data, we have unlabeled data, okay? So, which is to say, without giving any labels, the machine learning has to find some patterns in the data. So, unlabeled data just simply means that instead of this, what we had before, labeled data, we now have unlabeled data, which is to say, we just present the input X, okay? We don't give the model the labels Y or outputs, okay? The model just sees pictures and it doesn't know what is on the picture. And here we have two tasks. One is clustering and the other one is dimensionality reduction. So let's look at this. So clustering, what is this? Is basically just we have these data points, right, of which are unlabeled. What the model tries to do is tries to find a connection between data points and cluster them similar inputs together. Okay, so it figures out that maybe all of these apples are somewhat together, and we'll place them together and we'll put them into a certain cluster. Okay, and the same for pears and the bananas. Okay, so you find the patterns in the data and try to cluster it. Okay, so this is different to classification because in classification our data is labeled, right? And so what the model sees in training is different, right? Because the data is labeled. So that's why this is color coded, right? And here all is black. Okay. And then we have another task, which is a task of dimensionality reduction. So as the name suggests, we will reduce dimensions of the input. So we might have data which is very high dimensional. This is a super typical example in machine learning. So especially when we are handling images, right? If you take an image with your phone, you 1 megapixel, right? You have how many numbers for one image? Like a million, right? So a huge number. A million is a very high dimensional. If you put all of it into a vector, super high dimensional vector, okay? And so all of this, let's say data of images is very high dimensional. So here, for example, we have images of 3 different kinds of irises, which to me honestly look the same, but there are 3 different species. And this is super high dimensional, but we can project these 1 million numbers into or represent the same data in low dimensional space. So here, for example, you have projection to 2-dimensional space. So instead of using 1 million numbers, I just give you 2 for each data point or for each image. Okay, and I can plot these images on this plot, right? And I can color code them based on which kind of iris they are. Okay, and what you can see is that when we go to low dimensions, right now we see that there are some, like in this low dimensional space, there are still some distinguishable points between similar classes, right? They're all together, as you can see. All red is together, right? Okay, so the dimensionality reduction task is used, first of all, to visualize data. I mean, it's really hard to look at super high dimensional data. It's almost impossible, right? Or look at separate images together. We won't figure out anything. And we always want to understand. We want to understand what patterns are in the data. We want to understand what machine learning has learned, right? We want to understand what, let's say, if machine learning has learned something, we want to understand it, and so on. So a lot of the times we can understand it if we can plot it, visualize it, right? So easier. And in order to plot something, we need to project it either to 2 dimensions or 3 dimensions, right? And then we can plot it and visualize it. So dimensionality reduction is used for that purpose, for visualization, but it's also used for in connection to other algorithms. So in order to process 1 million numbers, right, it takes more computational time than to process 2 numbers. You can think of it, right? So if we want to have machine learning algorithms that do, let's say, fast predictions or fast image recognition or something like this, then it's very much useful to first reduce the dimensions and then do other kind of tasks. And then we can do, I don't know, regression, classification, whatever other tasks we want to do. So a lot of the times this is used in connection. And we'll see examples later. So we first do dimensionality reduction, then we do something else. And the dimensionality reduction has a point of reducing the complexity of the whole problem, making the whole problem run super faster. And we always have this idea, like, let's get predictions faster, right? So this is always the case. We want to have everything run faster. Okay, good. So this would be unsupervised learning. And then we have the last category, which is reinforcement learning. Okay, so in reinforcement learning, we don't really have data anymore. In fact, we have, instead of data, we have goals. Okay, and what we try to learn, or what the model tries to do, is it tries to learn what are good actions such that we achieve a goal. Okay, so this is the task, is to find good actions that will get me to the goal. Okay, so if we look at an example, so we might have this kind of problem that we have a rabbit in a labyrinth, and the rabbit has to come to the carrot, and this is the goal. Okay, so here we don't have data, we just have a setup, like there's a labyrinth of certain things and we place a carrot somewhere. That's it. And then what we try to do is that this algorithm will try to tax certain actions. Actions here means go down, up, left, or right. These are possible actions. Okay, and we try to see, or we try to reward the algorithm. So this is how it learns. We reward the algorithm when it does good actions. So for example, if the rabbit takes down, down, left, down, right, 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 up, right, down, and up, we got to the carrot, right? We will give it a reward. Okay, or if it got closer to the carrot, we will give it a reward. But if instead it took like down, right, up, right, then we will not give it a reward because it didn't get to the carrot. Okay, so we always have like this environment or a certain state where the rabbit is or what kind of paths it took. And then if it reached the goal or it's closer to the goal, we give it a reward. Okay, and then we repeat this, and this goes to the agent, and the agent, which is here the rabbit, takes the actions again, and so forth. Okay, so you can imagine this reinforcement learning is the backbone on any kind of chess playing machine, or any kind of games, right? So all of this like runs on reinforcement learning. Okay, because it's really hard to propose like, you know, the task is of chess, right? It's just like shahmat. There's no other way to pose how to pose the problem, right? So you only have a goal. You have no way how to achieve the goal, right? And so for this kind of games, the reinforcement learning is very much used. But don't think that it's only for playing games, right? It's also in science. You can also put scientific problems in terms of reinforcement learning. Like, let's say one example is, I don't know how to, there was one example that they use reinforcement learning in like how fish swim. And then they try to figure it out how like fish usually swim collectively, or if you want birds or whatever. And they try to like see how what actions are taken by individual like fish or swimmer in order to minimize their energy input that they have to swim, right? So you can, so don't think of this, you know, game kind of setup to only refer to games, right? It's used all over, and more and more these days also in science. Okay, so these were our three kind of classes and tasks that we distinguish in machine learning. But we can also distinguish something else, and this is, we can distinguish between discriminative and generative modeling, okay? So discriminative modeling means that we can just, as the name suggests, discriminate things, okay? So we can just discriminate whether an image is an apple or a banana, okay? Whereas a generative model can do more. It can discriminate things, but it can also generate the data. Okay, so this is what is why this is called a generative model, is because we can generate new data samples. In this case, I can ask the model to give me a new image of an apple. Okay, and this is also super powerful because we don't actually just, we can do, let's say, so much more in this kind of way, because we can do both description as well as generation of new things. And I will give you examples. Okay, so this is something like to get all different, you know, how we can categorize machine learning algorithms. And then for each category, we have super long list of methods, right? And this list goes on and on and on. Like I said in the beginning, we cannot cover everything in this lecture. And so what we will do is we will look at the methods here, okay? But of course, there are also a lot of other popular methods to solve the same task, which we will have to skip, okay? But if you go to some maybe other course in machine learning, you might encounter those. Typically, at least in machine learning, we try to discriminate a bit who does what, so all courses are not the same, okay? And this list is far from complete. In fact, probably it's like 3 times longer. I didn't fit in the slides. And apart from this, these are not even the neural networks. And then we also have the neural networks, okay? So in here in the neural networks, we also have a zoo of different models, okay? Like I said, these neural networks are distinguishable by, you know, how we draw these circles and lines. And so you can see that we can draw this in many different ways. And all of these things are doing different things. Again, we will not look at everything in this course. We will look at some of the basic kind of architectures. So we will look at, or we will briefly mention the perceptron from a historical perspective. This was, so to say, the first neural network. And so we'll briefly mention this. But the first neural network that we will talk about, and this is the most important one, is the forward fit neural network. This is a classical neural network. So if they don't tell you which neural network this, they probably mean this one. So this classical neural network is used for supervised learning and for these tasks of regression and classification that we had before. So we will look deeply into this neural network. Then we will talk about autoencoders. Autoencoders are used for unsupervised learning and for the task of dimensionality reduction. And then we will look at some of the generative models. So these are the ones that can produce data, new data points. And we will look at two architectures. One is variational autoencoder. So it's a twist on the previous autoencoder. And a different kind of one, which is called a generative adversarial neural network. And both of these models have, like I said, this ability to generate new data. So if you're wondering, you all know what are deep fakes, right? Okay, so what is running behind the deep fakes is basically these guns. Okay, so this, every time that you see this, or let's say AI or machine learning painted an image or something like this, this is all running on these models. So you know what is running in the background. Of course, again, this cannot, or it's not just used to produce fancy images, but it's also used in science, right? So there's always a connection. Okay, there are certain architectures that are really like known and common, but we will not cover them in this course because we don't have enough time. So one of them is the recurrent neural networks and various variations of that. These are used to cover sequential data, like to predict either in language models or like any kind of sequence, like, I don't know, stock market prediction, time, weather, something like this. Or convolutional neural networks we will also not cover, and these are typically used to handle all images. So every time you have an input as an image, you would use convolutional neural networks. We would. You can easily adopt new architectures, but we will cover the fundamental issues of all of these deep neural networks. Okay, so you can transfer the knowledge to new architectures, and even this list of neural networks here is incomplete because it was done, I don't know, like 5 years ago, I don't know how many years ago. And nowadays we have a new kind of architectures coming up all the time, right? Let's say we have transformers, which are very hip now, right? If you have heard of ChatGPT, right? This is the backbone that is running. Okay, but if you are interested in those two, you can also sign up for the block practicum that we have at the end of the semester or at the end of each semester. And then you will also learn about this too, okay? Good. Now, some prerequisites, or what are we going to discuss in this, or what all the topics that come into play in when we want to do machine learning. So first thing that I want to say is that machine learning is heavily based on math. So the basic people that do machine learning or hardcore machine learning, developing new architectures, whatever, they are in the informatics or mathematics department. There's a reason for that. It's heavily based on math. These methods, models, how we do them, it's all based on math. It's derived. It's not invented. Okay, so we need to know something about statistics or probability theory to understand why we approach and why we train a model in a certain way and not in another way. But you will, don't worry, you will have in exercise 1. So today you will have a review of probability theory. So you can catch up on the concepts like mean, variance, and Gaussian probability and so forth, which you probably already know, but it's good to refresh your memory. Okay, so this is in general important, but we also have some pressing issues here in terms of uncertainty and how to quantify uncertainties. Okay, so let's look into this a bit. So in 2017, there was a paper out that was quite interesting. And what they figured out is that the capacity of the neural network, capacity means how complex the model, or how complex the models are. And they said the capacity of the deep neural network is super large. What they showed is that they use like neural networks to try to classify 50,000 images into 10 classes of like airplanes, cars, birds, cats, and so on. Okay, now they try to do this classification. And when they presented the model, like the real data image and the true label, the model learned. Okay, okay, not surprising. But they also presented the model with random labels that just randomly labeled images, or they shuffled pixels, so was completely different image, or they presented the model with the random pixels. Okay, can you imagine an image with the random pixels inside? Okay, and in all of these cases, they showed that the model, basically, when trained, can learn and can correctly predict for all of these 50,000 samples. Okay, when we have a random image, pixels in an image or random labels, that means that the model could not have learned anything, but because there is nothing to learn. If you have a random data, there's nothing, there's no pattern there, there's nothing to learn, there's no correlation, nothing. So basically it means that because it was able to predict correctly for each point, it means that it memorized 50,000 samples by heart, learned by heart, because there's no correlation, nothing to learn. So that makes it a huge problem in general, because it means that we can have huge databases of 50,000 samples of images, but we can never be sure if the model actually learned anything, because obviously it didn't learn anything here. Okay, so this is what is known as the problem of generalization, and it's the biggest issue of machine learning also today, like all the time. Generalization means, can the model predict well for unseen data? Because I can construct a neural network easily that can predict well, perfectly for all the training data that I have, even if I have millions images, okay? But I can never be sure whether or not I have good generalization. Okay, so we will specifically look into that during this course, right? Okay, so in this case, like all of these neural networks that were trained, of course, drastically failed on the new image, right? They couldn't predict something new because they didn't learn anything. Okay, good. So that brings me to uncertainty, because we can never be sure whether the machine learning model actually learned something or not. We would like not to just have output predictions, like the image is an image of a cat. We would like to have a prediction together with an uncertainty. We want the model to tell us how certain or uncertain it is in a given prediction, okay? And to give us this uncertainty. Because it's not really bad if the model, has no idea what to do and just says, yeah, I think it's a cat, but I think it's a cat with 10% chance, Then I can simply say, okay, I will go back, I will look into the model more closely, or I will have a human classify this image, right? It's a huge problem if we just don't know which parts the model can correct with high probability or with low probability. So think about, there's a lot of the applications where machine learning is used, like in cases where you can do some serious damage, right? You have robots running around the factory, right? You want to have some kind of certainty before you lose the robot around, and it can cause some serious damage. So we always have like this issue. And it's also an issue for, in general, also if we don't have this kind of cases, right? We always want to know where the model is uncertain, and then we can go back and look at it. So what we will look at is Bayesian uncertainty quantification. It's a certain way how to do this uncertainty quantification. Good, so we have the statistics part, and then we have the part of numerical optimization. So as soon as we switch from linear models to nonlinear models, we don't have closed form solutions. We have to get the solution in training through numerical optimization. And then we need to figure out how to do this. So probably numerical optimization methods like Newton or gradient descent, you probably heard of them, right? Nevertheless, I want to again look into this, because in machine learning, you will see that in order to get things to work, okay, you will experience that during the exercises. A lot of the times you need to play with this numerical optimization part. And that's why I want to look at it more closely again. So you know what you're doing and you obtain a good model faster because you know what you're doing. And so we're going to look at this again, and we will also look at some special algorithms that are specifically designed for deep learning, for handling neural networks and for handling big data that you probably don't know. Okay, and then we have programming and computer science. So, I mean, it doesn't really mean much if you only hear all of these models, methods in theory, right? You need to actually be able to run them in practice. Otherwise, it's not so useful knowledge to you, right? So what we will do is that during the exercises, you will implement and program all of this into programming exercises. So you will see how to actually do this in practice, okay? So we will do the exercises in Python. Okay, so if we assume that you know something about Python, if you don't, we will have a short, a recap of Python. So you can catch up. So even if you never heard of it, but I assume that everybody has some knowledge of programming. That I think is needed. Otherwise, it will be a bit harder for you to follow. But the Python you will have in exercise the next time, you will have a review and you can always come and ask questions if you have problems, okay? So you can catch up, it's not a problem. But we are doing Python because nobody is doing serious machine learning in MATLAB, sorry. So it would be useless to teach you to do machine learning in some other programming languages when everything is happening in Python. Okay, so then it's also true that for Python, there were specific libraries for deep learning that were developed that make your programming of neural networks way, way easier, okay? So if you want to write your own neural network in C or C++, go ahead, but it will take you a week because you will have a lot of lines to write and a lot of debugging to do. So in Python, we have specific libraries. One of them is like PyTorch. The other one is TensorFlow. We will use PyTorch. And this makes these 1,000 lines into 10 lines or 2 lines even, okay? So it's way easier for you. And this is what is standardly used. So everybody's using this. So after the course, you will not only know something about machine learning in theory, we also learn machine learning practice and in practice such that you can directly use it in a very relevant academic or industrial field, okay? So it's useful for you. Good. And then lastly, of course, we want to connect all of this and look at specifically machine learning in connection to problems that we are interested as engineer or as a physics student or chemistry or what not. So in terms of scientific domain, okay? And here we want to look at how can we incorporate physical laws into machine learning. So inform a machine learning model that there is some physics that we want a machine learning model to obey. And how can we do that? Okay, so of course we have many kind of different theories, okay, not only those listed here, but just as a reference. Okay, so we can pose like quantum mechanic theory, we have classical statistical mechanics operating on the atom kind of level, we have, I don't know, fluid dynamics operating on a meter kind of length scale, right? These are all kind of different theories that we can work with. And typically, because these theories are complex for kind of any kind of real kind of case scenario, we don't solve this on paper, right? But we solve it computationally, right? And we run simulations. And for each kind of theory, we have our own, class of simulations that we would use in order to solve this classically. Okay. Nevertheless, all of this, right, across different scales, so to say, we always have this problem that whatever simulation we look at, it's always not fast enough, and we always want to make it cheaper, better, faster, so we can run more simulations, so we can discover more, right? So we always have this, that we wanted to make it less expensive, okay? And that we want to make it more accurate. So this is always somewhat related or some compromise typically in classical simulations. So a lot of the times in machine learning, right, our goal will be to obtain faster predictions of higher accuracy than we can with classical simulations or with classical, say, engineering modeling, okay, also beyond simulations, okay? And we can do this in different ways. So the question is how we can combine now our classical machine learning that is used to classify images and some scientific domains of physics and physical laws, okay? So there are different kind of ways that we can go about it. We can use only the data, okay? So we can present to the machine learning model just the data itself. So this is, so to say, equation-free approach, just data. And we kind of expect the model to figure out that there are some laws, something in the data, okay? And to some extent, machine learning model will learn this, okay? So that there is some, I don't know, physical law behind it. To some extent, we will learn this. But it's better if we give more information to the machine learning model, because then it's easier for the machine learning model to figure this out, okay? And so then we can have a combination of data and physics, okay? So we inform machine learning model about our physical laws. And we can do this either approximately or by construction. We will see later the example. So approximate means we approximately will satisfy this physical law, or by construction means we will definitely, 100% satisfy this law, okay? And we also can distinguish how we approach this, let's say machine learning model versus, let's say simulation or prediction, okay? So we can either do a direct prediction, which is to say, we're not going to run any simulations, we're just going to predict directly with machine learning the output of the simulation, or some kind of result, okay? So let me show you an example. So let's see an example from fluid dynamics where we have only data and we are trying to do direct prediction. So this is an example. So here we are trying to predict lift, drag, and moment coefficients on an airfoil based on the shape of the airfoil. So we might give to a machine learning model as an input, we give it a shape. So this with these numbers encoded. And then also something about the fluid flow around it, like angle of attack, Reynolds number, Mach number. And then directly as an output, we want to obtain this lift, drag, and moment coefficients, okay? And then typically or standardly, this would have been done. You would have a shape of airfoil. You would pass this to a simulation. You would do some computational fluid dynamics, right? You would get your simulation. You would, from that data of simulation, compute lift, drag, and so forth, then get the result, right? Here we bypass all of the simulation. We just directly teach the model to predict this directly. And of course, the use of this, right, is in terms of airfoil design, right? We want to optimize this to have, I don't know, minimum drag, right? As an obvious example. Okay, so this will be from fluid dynamics. We can switch to a molecular system and look at an example here of, again, direct prediction using only data, no physics. A famous example here is prediction of protein folding. This is, so to say, an open question for many years. And then Google and actually also one group in academia, they basically almost simultaneously solved this problem. So Google published this AlphaFold. And this model, what it can do is it can from the sequence of amino acids. So if you know, proteins are a sequence of amino acids. We have 20 amino acids in your body, and the sequence matters, and the result will be different. Okay, so the result meaning the structure of the proteins will be different. So this is a super hard problem because in general, the average protein length is like 300 amino acids, and for each one of them, you have 20 options. So it's like the number of possibilities you can calculate in your head is like to the power of 300 to the power of 20 or so. So it's a number you cannot think in your head. It's like so huge, impossible to think about. And the problem is always how to get the prediction from the sequence to the folded structure. And they managed to get quite a good prediction. So this was a lot in the news. So that's why I'm mentioning it. Okay. So this is another example from molecular kind of scale. Okay, another example from, let's say, material design. So, for example, in material design, we want to optimize the material in some way. So what is popular material nowadays is called metal organic frameworks. They have been proposed for many kind of different things like gas storage, separation, purification. So a lot of things, green energy, right? How to store hydrogen, how to, I don't know, get CO2 out of the atmosphere and so forth. A lot of these applications in terms of green energy. And also like in terms of medicine, like drug storage, catalysis, like how to do better batteries and so forth. So the problem here is that, again, it's chemistry. So you have, it's a combinatorial complexity of whatever you can do, materials that you can think of to do. So here, they have like specific like kind of structure of metal organic. So it's a metal node with organic linkers, doesn't matter. The number of possibilities is so huge that, you know, again, it's unthinkable to try everything. You just cannot do it. But again, we can use, let's say, machine learning here in order to help us, right? So here is an example of we're doing direct prediction, but we're using data and we're adding physics to it, okay? So for example, in this case, we are trying to predict the charges on the molecules, and we need these charges in order to process later on for, it's like an input in order to figure out cases like how easily, I don't know, a gas will be separated in a MOF. But here we have a physical constraint, is that the whole MOF should be net neutral. Okay, so this is something that we know from physics and then want to incorporate into the model. Okay, so this is an example where we don't just use data, but we also incorporate the physical restriction that we want the sum of partial charges to be zero. Okay, so this is how we can combine these two. All right, so these are some examples in terms of direct predictions. We're not doing any simulations. But we can also use machine learning in combination of simulations or in terms of to replace them, okay? So we can use, so to say, machine learning driven simulations, okay? And this we can do in machine learning, can either in full replace the simulation or in part, okay? So instead of doing simulation, we can instead do a machine learning model. This machine learning model will give us the same information that a standard simulation would give us, okay? Now let's look at some examples here. Okay, so one of the examples, let's say, that we did is from a molecular system. We have in general, in molecular system, we would run simulation called molecular dynamics. It's just a snapshot of how the molecules evolve in time. Okay, and here we did a test on this alanine dipeptide. It's just a molecule, it's kind of like a typical test case for also protein folding and dynamics. And it looks like this. Okay, so in typical simulation, this molecular dynamic simulations, you will get a trajectory, what's called, or a time series of how these molecules evolves in time. Okay, what it does. Now we want to use this data in order to train the model to give us the same kind of thing, to be a simulation, a direct replacement for simulations. Okay, so here, let's say we used autoencoders. So basically we did dimensionality reduction, and then we use some neural networks in order to get these forward predictions. And we trained this model in order to give us exactly the same. So in a step-by-step fashion, we would get what is the structure of this molecule at the next time step, and next time step, next time step, and next time steps, the same way as in simulation. And of course, from this trajectory, we can then compute any kind of properties that we are interested in. Typically, like in these cases, we are interested in how fast the protein goes from one configuration to another configuration. This is related to protein function, how the protein function is related to these dynamics. Let's say if you have like protein, some part it's opening and closing, and then something else can bind to it. Right? This basic functionality. Okay, so here, for example, is a case where we use only data. So this basically learned physics of molecular simulations from data only. Okay, but we can also add physics. Okay, so to show you this, from let's say fluid dynamics, okay, we can use data and we can push the model to satisfy a given partial differential equation. Okay, and these are the so-called physics-informed neural networks. Okay, and you can see here the results for some test case systems. So one is Berger's equation. Berger's equation is like a test case system you want to solve for aerodynamics, or so aerospace. It's a basic equation of gas dynamics. It's a hard case to solve because this Berger's equation leads to a shock under certain conditions. Shock is like a discontinuity. And to model this discontinuity is hard. That's why they use this case as a test case, right? Before you can do something serious like predict a rocket, right? You should be able to solve this. Okay, so here basically we have this physics-informed neural network kind of structure. We have as an input, we give it, tell the position. So here is in 3D position and time. And as an output, we want to have the velocity profile and the pressure. Okay, but we don't train this model just with data. We use also the information of partial differential equation, which is to say, we know which partial differential equation the machine learning model is supposed to solve. Okay, like Berger's equation, we know the partial differential equation. If we want Navier-Stokes, we know the equation, right? So here we basically will give this partial differential equation to the model, okay, and we will push the solution to solve this equation. Okay, so this is an example of approximate physics because it's not constrained, but it's pushed towards this solution. Okay, so we will be close. Yeah.
If I understand correctly, you need the simulation, the numerical simulation for training. Okay?
Just to get the data.
Yeah. What's the benefit of the network? Because I understand that it's basically in the end it can predict like other data points that we didn't use for training.
Exactly.
But does it work on a different domain, or is it just the domain where it was trained?
Yeah, this is a very good question. Typically, it depends. What do you mean specifically by domain? Like, let's say.
Okay, so like here I have like a very restricted spatial domain, and I pick some data points from a numerical simulation.
Yeah.
And I use these for training.
Yeah, it will be.
I can predict the solution like somewhere else in this domain.
Yes, that works.
Same boundary or initial conditions.
Exactly.
And if I would change this domain, like slightly change some boundary conditions, like would it still work? Because I understand it would.
Yes, it wouldn't. In a classical example, it wouldn't. But you can like modify this basic thing in order to make it work and make it transferable to some extent.
Okay.
So it was just, do you train on one boundary condition? Do you bring multiple models together into one? You can do that.
The model would learn, like, depending on the conditions that I give.
Yeah.
It would predict it.
Yes, but you have to then modify this. Would not be so simple. It would. You have to.
The boundary and initial conditions, one of the loss terms. Like, by training it, like as I understand it, I have like 3 different loss functions. One that like has boundary and initial conditions. One for the like numerical data points where I compute some kind of difference there.
Yeah.
And one that incorporates the physics, like the PDEs.
Yes.
And now when I change the boundary conditions, basically I would change one of these loss terms and I would have to train, like start from a new one.
Yes, but like I said, this would be the way you explain it is exactly in the basic form like this, but there are methods that were extended like apart from this that also had this like difference.
So it's
And then
possible to transfer to different domains.
yes,
And use
you
pre-trained networks to adapt to new.
yes, it is possible, but you will not do this in this course. In this course, you will do this, and it's not going to be transferable.
But like, to this extent where we do it, has it any benefit over numerical simulations? Is it more accurate? Is it like?
Yeah, in certain cases, it can be more accurate. So, and also you are just training, you can only train on the boundary and initial condition, not the solution inside, which is something that, so you don't need a simulation. That's also possible. So then you would solve it, yeah.
We're also going to look at like inverse problems with from neural networks where we take the measurements, we know the governing equations, and basically we don't necessarily use the numerical simulation data, just we use the measurement, and then we predict some other quantities. So
for example, I have like a measurement of concentration of pressure, and we can predict other like velocities.
Yeah.
Okay, maybe we are getting ahead of ourselves, because we will discuss all of this later on. All right, good. Then if we go to same thing, like trying to connect data with physics, but from a different domain, let's say from a molecular domain. So here we can connect this and we can model this, or we can add physics by construction, which is to say we modify the architecture, or we set the problem such a way that physics is constrained to satisfy certain laws by construction. Okay. So as an example, and something you will do, we can look at classical mechanics. So in classical mechanics, we have a problem of, how the m-particle systems evolve in time, and we can model this. In order to see that, we have to solve basically Newton's second law. Okay, we have forces m times acceleration. Okay, and then, but instead of solving these equations, what we can instead solve, we can reformulate the same problem into what's called Hamiltonian formulation. Where we construct a function which is called Hamiltonian. It's composed of kinetic and potential energy, and together this is the total energy. And in this formulation, we can define different differential equations that we have to solve. And like I said, it's an equivalent problem to solve. Okay, but these equations, they have some specific structure and some specific properties, like energy conservation and that they are time reversible and so forth. So when we try to now get a machine learning model to solve now a molecular system, how it evolves in time, we would like it to also conserve energy. This is like a fundamental property that we, strictly want to, let's say, conserve. And we can do this, and we can formulate the problem in such a way that we will constrain this. Okay, so for example, you will doing the exercises, you will do something that's called Hamiltonian neural networks. Okay, we pose the model in such a way that we strictly conserve energy conservation. So this was shown originally on some very simple cases, like either mass spring system or pendulums or something like this. And then you have a comparison between like standard thing that you can do and something that incorporates physics. So these are these Hamiltonian neural networks. And in the case of when you incorporate physics, let's say you conserve the energy like almost exactly, right? And in the standard case, you will not conserve the energy. Right? Okay, so this is another example. So this was examples where we basically replace the full simulation with machine learning. Okay, but we also have another kind of setup that we can use, is that we can only use machine learning, or we can use machine learning only for one part of the simulation, which is to say, don't replace the whole PDE, but just one part, the part that is hard, okay, typically, or expensive or something like this. So this would be like a combination, like partially we solve classically, partially we use machine learning for. So a few examples here. So let's say in the fluid dynamics, and let's say in turbulence modeling, we have this problem that at high Reynolds number, with highly turbulent systems, If we want to get a really good solution, very exact solution, we have to put a very small grid in order to resolve all the scales, right? This is called direct numeric simulations, resolving all the scales, and this is computationally expensive. Of course, we have also simulations that are cheaper, but not so accurate, okay? So for example, this would be this Reynolds average Navier-Stokes or large eddy simulations, if you ever heard of that. So what is a thing in these models is that they introduce some kind of model of turbulence, okay? Now, of course, because this is a model is not correct, and in fact, we don't know what kind of model to present, okay? So now the idea could be, okay, the things that we don't know, like this turbulence model, let's replace that, or let's use machine learning to help us here, okay? So this is the idea here. So we would use this runs, so this not so accurate simulations, okay, and get some flow features here, and then we would use high, like very accurate simulations to get the stresses, and we would use this data to train the model. And then in testing, so we can get an idea is that we can get this machine learning model to basically predict this turbulence model. And with that, we have a cheap simulation for high accuracy, okay? But obviously, we are still like, we are combining, right? Some simulation part, some machine learning part. So one part is coming from machine learning, one part from simulation. Okay, and just to give you another example, we can also do this in terms of molecular systems. So this would be physics by construction. So like I said before, in molecular dynamics, we are solving Newton's law, like, and the most hardest part here, so the solving this numerically, this Newton's law, this is easy, this computationally inexpensive, we know how to do this well, not a problem at all. What is a problem is that the force is a negative gradient of the potential energy, and we have no idea what to set for a potential energy. This to us is unknown. We can go to quantum physics, but there we cannot really solve anything apart from hydrogen explicitly. So we also have to do some modeling. And this is super computationally expensive, right? So you cannot really do anything, like 100 atoms is already too big. So then we want to replace this part that we don't know. It's super hard for us, cannot figure out. Let's replace it with machine learning, okay? And then we can propose architectures that respect the invariance of potential energies. So we know some things about potential energy, like it's invariant to rotation, permutation, and translation. And we can incorporate this directly into machine learning so that also our model is invariant to translation, rotation, permutation. Okay. So for example, here, this is an example from our group. We did this and to obtain a potential energy model here for a model of for the problem of diamond. And so we use neural networks. So here there are graph neural networks, another kind of architecture. And what we are able to do is we are able to train this model such that the model will predict correct mechanical properties of diamond at the same one as measured experimentally. So we are training what model should we use for potential energy in order to observe the same kind of properties of this material. Good. So these were some examples, like I said, just to give you a feeling of what you will see in this course. Now, what we talked about so far is like examples where we use data only to figure something else, or data in physics, right? Where we put physics, like a partial differential equation, into the model. But there's also another way, and we can get physics from data, which is to say, we can use data to train the model, but the model will, as an output, give us a partial differential equation, for example, which is to say, now we can learn physics, you know, if we didn't know it before. Okay? So for this, one way how you can do this is with so-called sparsity promoting machine learning models. So one method in particular is called Cindy, and this is what you will do in the exercises. And also we will look at the sparsity promoting algorithms during the lectures. So for example, they showed for the Lorentz system is this set of differential equations. And Lorentz system is a typical chaotic system. So before you can predict the weather with machine learning, you should be able to predict Lorentz system. It's like a typical test case. And so they showed here that training on data from the Lorentz system, they can actually, from the model, figure out the equations back, okay, without presenting these equations to the model. Okay. Good. So now that we know something about machine learning, we can look at the course content and what we will learn here. Okay. So for session 1, we are almost done. We have 10 minutes left. So we have a check here. Okay. So what we will do next time, we will look at the problem of regression. We will start with the problem of regression. And then in session 3, we will look at the biggest problem of machine learning, generalization. This is the biggest problem for all machine learning, right? And we will look at what is this and how we can cope with that, okay? Then we will look at uncertainty quantification, right? The thing that we don't try to just get a prediction, but we want prediction with uncertainty, right? So the model, we want the model to tell us how sure it is of certain prediction. And we will do this with Bayesian uncertainty quantification here. In lecture 5, we will look at the sparsity of our learning, so how to get physics equations from data. And then we will here somehow switch from linear models to nonlinear models, so we will have to look at numerical optimization. Okay? And then we will look at another class. So all of this is going to be more or less in the setup of regression. And then we will switch briefly to classification task. Okay. So all of this is, let's say, supervised learning. Okay. And then you will see for everything that we will do, we will first learn things for linear models and low dimensional data. Why? Because low dimensional data we can plot. You can see how things work. You can get deep understanding of how the method works. And then we're just going to replace linear model with non-linear model. And typically the switch is going to be to neural networks, which are non-linear models. And then we are going to have to rely on all the knowledge that we have learned in the simple cases, linear models, low dimensional data, and work there, where we will be more or less blind, because you cannot really imagine or like visualize high dimensional data. You have no idea what's going on, right? So this is always like, we're going to learn stuff on the simpler cases, then transfer it to the nonlinear neural network, deep learning kind of case. So this would be for the supervised learning. And then here in session 9, we will look at deep learning tricks. I call it deep learning or neural networks. It's not something new, it's not like it was invented 20 years ago. It was invented quite some time ago, but nobody really knew how to make them work. So they all know that theoretically this could be powerful things, but nobody made these things actually work, like actually give good predictions, okay? There were a lot of years had to pass by and a lot of things had to be figured out. They're called tricks to make this thing work. So we will look at this, and this is now a standard practice, okay? And we will look at why certain things are done. Good, and then in session 10, we will switch to unsupervised learning. We will look at dimensionality reduction with the linear model, and then switch non-linear model. And there is a direct correlation between these two methods. And then in the last 2 sessions, we will look at generative models. We will look at how to generate new data or new examples from the model itself. And we will do this with 2 methods that I said. Okay, so for the literature part, if you want to buy a book or get a book from the library, the first book I would recommend is this first one. Bishop is a classic textbook. Okay, it's really nice to read. It's like readable. It's nice. A lot of the material is also from here. So it's, I think, the best reference. Unfortunately, there are not everything covered here. Let's say some bias part is missing, some sparsity is missing. And then the next book to look at would be this machine learning. And then if you want maybe some more topics on deep learning, specific generative neural networks, then you can look at this second book. On Moodle, you will also find extra reading. So sometimes if you look at the Moodle, So for some sessions, I give you some extra reading, like here, further reading, right? And I give you some articles where this is from. And you also have in the beginning, you have some examples of reference machine learning applied to physical modeling and simulations, where you can see, okay, where is this used, what people have done, okay? So it's just to get an idea. Like I said, there is a ton of papers that I could give you, but this is just a sample, right? Then you can go from here. And then regarding the course organization, so the lectures will cover basically theoretical background of machine learning and all material you will find on Moodle. So like lecture notes and links to videos. During the exercise, like I said, you will do programming exercise and Anna will explain everything about this. And for the exam, we already know the date is written on Moodle. It's a closed book exam, so just pen and paper. And if you solve exercises or you submit exercises, then you can get a bonus to your grade, okay? The maximum bonus that we give you is 0.3 grade bonus to the exam grade. You get this irrespective of the exam grade, and this bonus is transferable to any kind of later on. So if you do the exercises in this semester, you can use this bonus in any other future semester. Okay, good. So with that, are there any questions about the organization? I think there is one. We have some questions on chat. So do we have practice session today? Yes, you already answered. Okay. So, okay, then this is clear. So today you have your first session and you will do some review of probability theory to refresh your knowledge. Okay, then for the remaining 3 minutes, I want to say that on the Moodle, you will also find here link to interactive demonstrations. And if you go to this link, you will get to this page. And here we have some demos that you can play around in order to understand the course better. Okay, so the first one that I want to check is function fitting. Okay, we have some data and we want to fit this data with some function. And we want to see what the result is. So here in this demo, you can choose different kind of models that you can fit, different functions that you can fit your data with, and you can choose different kind of norms of how to fit this. Okay, so and then you have different predictions, and you can see how this works. Okay, also if you refresh the page, always you will get new data. Okay, because this is running on a server, it's actually solving this as you interact with it. So I want you to look at this as a preparation for the next course or next lecture. And in the next lecture, we will try to answer these questions. Okay. You also have some more text if you want regarding function fitting and this demo. On your last page of the lecture notes. Okay, so you can look at this as a preparation for next time. Next time we will discuss these questions. Good. So you will know how to answer. Okay, good. Then let's stop here. There's also one more question. Would we also have exercises to solve by pen and paper? I ask as an exam will only be pen and paper. So all of them are computational, right? Yes, all of the exercises are computational, just because we want to teach you something not only for the exam, but for real life. I want to prepare you for the real life. So after this course, you should be able to get anywhere and do some serious machine learning in your domain. That's my goal. And for that, you need to know how to work with this, like not theoretically, but in practice. Okay. And for the exercises for the pen and paper, we have the, on Moodle, you have the exam, like mock-up exam, so you can see what kind of exercise you can expect. And sometimes in lecture notes, we also have some examples which are pen and paper, so you can also work through that, okay? So this should help you with the exam. Okay, and we will have at the end, last exercise will also be about exam preparation. So you can see what you will solve together the exam, and you can see what kind of exercises to expect there. Good. And then really let's thank you very much for joining in today.